Okay, so hopefully you got access to the live stream from Wednesday, since the live stream from Tuesday kind of screwed up several times actually. But we basically did the same thing where we created this database to support this annuity, the stock, and person classes. Where we have a one-to-many relationship from the person to the email table. We have a one-to-many relationship from the person table to the account table, because more than one person can own because one person can own more than one account. And then we previewed what we were going to do last time, where we said that, okay, well, wait, maybe I want instead that one person can have many accounts, but also one account can be owned by multiple people. Right, so what I want is a one or many-to-many relationship from the account to the person table, and to do that, we're going to have to redesign this and put a join table in between this. So let me go ahead and start by just getting rid of all of this stuff right here. I'm going to retain that account table over there for now, but like I said, we're going to have to put a join table in between them. And so let me go ahead and start by designing that one. All right, there we go. All right. Let's clear that out. All right, so following the exact same patterns that we did last time, what should we do here? What's the first thing that we should do? What's the first thing that we did in every single table up to this point? A primary key. So first of all, actually, the first thing we need to do is what? Name this table, right? So what would you call this table? Remember that it's connecting a person to an account, right? And so that one person can own many accounts, one account can be owned by many people, several people. So what's the operative word that I had in there the entire time? Owns, or ownership, right? So, or you could say, it is a common pattern to do the following: person, account, right? That you just take the two table names and you shove them together like that. Or is it account, person, right? I prefer to name them what they're modeling though, right? And in this case, we're modeling ownership. Ownership. All right. You could call it owns, but that looks like it works one way. Or is owned by would work the other way. And both of those are nouns, and we prefer, those are both verbs, excuse me, and we prefer nouns. So I'm going to go ahead and call this ownership. And that means that I will have a ownership ID for my primary key as an integer here. All right. Now remember that I want to bring these two things together. I want a many-to-many relationship between the person table and the account table. That means I'm going to have to put in two foreign keys. I'm going to put in the person ID, which is going to be a foreign key. And that's going to end up causing this kind of relationship, right? A one-to-many relationship from the person table to the ownership table. And then I'm going to put in a second foreign key, account ID. Right? And that's going to be a foreign key to the account table, giving me this relationship, right? A one-to-many relationship there. Now, effectively, between these two tables, we end up having a many-to-many relationship here, okay? That's what bridges these two tables together, or like we said, this is a join table, okay? Now, is there anything else that we might want to put into this table? Question mark, question mark. I left plenty of room here. Let's think about that. But first, let's go back and actually program this, okay? Let's zoom in here, all right? Remember that we have an account table, email table, person table. And because this is going to join two of these tables together, these tables have to exist first. So I need to go down to the bottom here. Right? And let's go ahead and create an ownership table. Right? Represents an ownership. Right? A many-to-many relation between the person table and the account table. Okay, so create table, if not exists, the same patterns as we did before, if not exists, and I'll call it ownership. Right. There we go. Opening parenthesis, closing parenthesis, semicolon there. And I'm going to put those three things that I already identified: ownership ID, person ID, and account ID. So ownership ownership ID. And I'm going to steal some code up from here because remember, this is the pattern you're going to follow all over the place. Int, not null, primary key, auto increment. Okay, that's my ownership ID. Then I'm going to have a person ID and a account ID. And these are going to be integers, not null. Integers, not null. And then finally, I'm going to have to make both of those foreign keys. Now remember, the way that we make a foreign key is at the end we say foreign key, and then what's your foreign key? The person ID, right, is going to reference or references the person table and the person ID in that person table. Now because we have two foreign keys, I'm going to have two statements here where it's account ID and the person ID, not person, but account and account ID. There we go. Okay. All right. Now, this gives rise to a potential for some data anomalies. For example, what if I had, let's go over here. What if I had person A? All right, now this is just one person. And there was an account, 1, 2, 3, 4, right? What if I had two entries here? Let me go with another color here. Person 1, 2, 3, 4, and then account number A, B, C, D, right? Okay. Now what's to prevent me from having two entries like that in this table, right? This is what uniquely identifies the table, right? This is going to be unique all the time because it's auto increment and it's a primary key. But these two things together, right? There's nothing to prevent me from saying that person 1, 2, 3, 4 owns account A, B, C, D. Person 1, 2, 3, 4 owns account A, B, C, D. Over and over and over again. I could have like 5 entries giving me the same relationship between that person and the same account. I want to prevent that. All right? So what I'm going to do is I'm going to put a unique key on the combination of those. So remember, how do we do unique keys? Where is our unique key here? Actually, I might need to do a little bit different syntax here. Oh, I'm on the wrong page. All right, so where is, should be here. Oh, darn it, do I not have it? Oh, well, that's all right, we can do it. Find unique. Okay, so we'll just do it from scratch here. Hopefully I can remember the syntax. But we'll say unique key, right? And here we're going to have a combination on the person ID and the account ID, right? Account ID. Right? Let's see, does that work? Unique key. It's liking it, but let's go ahead and run the entire script and make sure that that actually executes there. Oh, perfect. All right. Create table if not exists, and it's going to be a unique combination. So it's going to be a unique key on two things. So that the combination of 1, 2, 3, 4, A, B, C, D, that combination there has to be unique. Now there's nothing to prevent me from doing, say, 1, 2, 3, 4 also owns X, Y, Z, right? Because the combination of those two things is still unique. The first one matches, but the second one doesn't, right? So that allows me to still have one person with multiple accounts, but also it allows me to have, say, multiple people, 5, 6, 7, 8, and A, B, C, D. Now that says that two people, this person and this person, owns this A, B, C, D account, right? By putting that unique combination on that key there, though, I am prevented from having like this as a duplicate here, okay? So that looks like a pretty good design. Now what I want to do before we move on is to come back and remove those old foreign keys. Let's go ahead and remove that old foreign key here. And I'm going to remove the person ID that it was referring to. Right? Now what did I just do there? Basically I said it's not going to be this relationship. It's going to be this relationship now. Okay? Let's go ahead and generate an ER diagram based on this so far. Okay? Do we remember how to do that? You're going to want to generate an ER diagram eventually, right? So you can always go up to new model, right? And then file, import, and reverse engineer the script that I was just writing. So this exact same script here, 156, place imported objects in a diagram, execute that. Oops. Uh-oh. Okay, whatever. Close. All right, it still worked. I don't know what I was complaining about there. But, oh, okay, no, it didn't work because we do not have our account here. So let's go ahead and get rid of that, Don't save the, just like yesterday, it's going to crash now because just closing something crashes apparently. All right, so let's make sure that it's still, it was complaining about some, maybe I fat fingered it somewhere. Yeah, I did. Oh yeah, that's right. Of course, I made changes to it. I took out the person ID here, and I took out, what else did I take out? I took out that one, so I need to get rid of that comma. That's what it was complaining about. All right. All right, so save that, and let's run it one more time to make sure everything works. Can I delete? Okay. Oh, and then what did I forget to do up here? Because I added a new table, I need to also drop that table. And since I added it last, it needs to be deleted first. Right? Drop table if exists. What do we call it? Ownership. There we go. All right, now execute the entire script again. I see green everywhere. Wonderful. Now let's go ahead and create a new model. And then import reverse engineer script, this 156 script, and place imported objects on a diagram so that we can see visually what it looks like. Right? Yeah, okay. There is our new design. We still have a person with an email, but now the account and the person look like we designed it over here, right? There is one person can own multiple accounts, and one account can have multiple. Google, there's their name, and they own 50 shares, and each share is, I don't know what Google is right now. Everything's tanking right now anyway, so let's just say 150 bucks, right? All right, now let's say that Jane here, she also owns a stock, the exact same stock of Google, right? At 50, say that she's got 100 shares though, 100 shares. And for some reason, we have a different price on it, $149, right? That's because over here in the account table, right, we keep track of those pieces of data. The name, in fact, let me go ahead and change the name here as well. Google, right, with an L at the end, right? Because I am storing it in the account table, there is no enforcement that, well, this is the same stock as this over here. It's just that Joe owns 50 shares and Jane owns 100 shares, right? So what's to stop me from saying that, I'll spell Google one way in one record, spell it a different way in another record, and also give rise to price differences, even though they're the same stock, right? Is there a way that we can prevent this?
Could you create a new, like, if a new stock name gets submitted,
Okay.
like, does it have, you could create almost a table that would, like, have to match it, and then it would check, like, the pricing.
I want to make sure that these two stocks are essentially the same.
Right.
So that if you, there's already a Google stock with a price of 150 bucks. If you try to put in another Google with an L and $149, no, I'm not going to let you do that because that's not the same thing, right? So I'm going to try to combine them over here in the account. What's the difference though? The real difference here is this piece of data, the 50 and the 100, the number of shares. Does that really belong in the account table here anymore? Probably not. Where does it belong? I own 50 shares of Google stock. She owns 100 shares of Google stock, right? Not this one, sorry, but over here, right? That's an ownership thing, right? So let's go back over here to our design and let's think about, okay, well, what here, and I'm going to use a red here, the number of shares, that is something that should probably be over here in the ownership table. Because when person A owns Google stock, they own 50 shares. 50 should be over here. Right? Because not everybody is going to, either everybody's going to end up owning 50 shares, and you own 50 shares, and I own 50 shares, and they own 50 shares, or we're going to have to repeat data over here, right? We're going to have to repeat the name and the share price, okay? Now, name and share price, those are invariant with respect to every single type of stock, right? But what about the annuity here? Right? Do you have cause for putting these over there? Right? Now, annuities are kind of different because every annuity account is individual, right? There's no such thing as a Google annuity account, right? Just like there's a type of savings account that you could have, but everybody's account is completely different, right? We could all have accounts at Wells Fargo for savings accounts, but all the balances are different, all the account numbers are different. It could be like the same type of account, like ignore. Right? All right, and come back over here. And now let's clean this up a little bit, right? I'll leave everything in as we've gone along, even including the stuff that I got rid of, just so that you have it, right? And including these constraints that are not enforced. But now in my account, where's my account? There we go. All right. I am going to have to take out not share price, but number of shares here. Okay. And then I will put that down over here for stocks only, stock types only. Right? Now you might have an argument here for, well, we also need to know what type it is over here. So count type varchar 1 not null. Right? But then that would give rise to potential for other data anomalies. What happens when the account type over here somebody puts in S, but then up here somebody puts in A for that account type number when you're making a connection to it, right? So I don't like the idea of redundant data. In fact, that's why we do relational database management systems, because we are reducing redundancy. So I'm not going to put the type in 2 places. I'm going to put the type in 1 place, okay? Otherwise, there is a pretty good final design there. And you'll know that it's a pretty good final design because, as we said before, to do enter some, or insert some test mock data, right? And to do write some basic queries to give your database design a workout, right? And that's what you'll do, not after the break, after the spring break, you'll be designing your database and you'll be writing like 15 queries like you did this week for the albums database, but you'll be doing it for your database, right? So you've got to make sure that there's plenty of data in there, right? I basically did the absolute minimum here, but you'll do more, okay? All right, questions on database design? Otherwise, at this point, I will go ahead and put that in as our final design. And you might need to come back and rework it if requirements change or whatever. But what I wanted to do is I wanted to make some observations about that entire process. Okay. Again, like with class designs, semantics will dictate your design, right? If I tell you that you have to model an annuity, a stock, a person, and their emails, right? I'm basically kind of giving you, well, there's got to be a table there for persons, accounts, and emails, right? And it's basically a 1 table per entity strategy, right? There are, of course, some counter examples to that, but that's a general guideline, right? Some style tips: be consistent in your naming conventions. Right? Do not pluralize table names, right? Or column names. Tables, the modern convention is that tables should be upper camel cased. Right? And then the other modern convention is that columns should be lower camel cased. Now, why do you think that is? Why do you think I'm following that modern convention? If you create a person table, and it's capitalized and it's upper camel cased, what is that going to match in your Java code? It's going to have the exact same name, right? What about all of your member variables, right? All lowercase as well, right? In other words, I'm following a convention that will match exactly to my Java classes, okay? So that's why we do it modern. If you want to go old school, you can. Old school would be, lower underscore casing for columns, and really old school would be like all upper underscore for table names. Don't do that, right? Again, you're going to cramp up your pinky finger holding down the shift button all the time for those underscores and for the all caps, right? You probably shouldn't do that, right? Let's see, avoid abbreviations. We didn't have any abbreviations that I remember except for a UUID. So avoid abbreviations unless it is well understood, right? For example, UUID, right? Of course, UUID is going to be well understood. So maybe social security number or maybe NUID, although that one's a little bit less clear, right? If they're within the NU system and they're working on an NU system, then of course they're going to know what an NUID is. But if they're outside the system, then what the hell is an NUID, right? It's a Nebraska University unique identifier, right? Okay, so table names, let's see. Other conventions here, make sure that every table, and I'll bold this, every table has a primary key, PK, that is an integer. Don't use doubles or varchars, right? Now, why is that? Integers are exact, right? Go to any programming language. If you take 1 divided by 3, that gives you 0.333333. Add it 3 times. Does that give you 1 necessarily? Nope. It could give you 0.9999999, right? In other words, there are floating point errors that you only have about 16 digits of precision with a double. If you're using a key that's supposed to be a unique identifier, then what is the difference between 1 and 0.9999999, right? Don't get into that. What if it's a varchar, right? Like a UUID or something, right? Well, what if it's a varchar with all caps? So because it's a hexadecimal, A, B, C, D, E, F, right? What if those are all caps versus what if they're all lowercase, or what if there's a combination? In other words, case sensitivity issues come into play here. Not only that, but things like character encoding, like UTF versus Latin versus ASCII text characters. There are just a whole bunch of cans of worms that you're opening up when you don't follow this convention, right? Also, there's going to be way more inefficient. Comparing an integer to another integer, immediate, right? But comparing a double to another double or varchar string to another string, those are way more computationally expensive, right? So make sure that it's an integer, right? Use a name that is the table name plus ID, right? Why? Because now you know what the primary key of that table is. If you know the name, ownership ID, person ID, etc. Right? Foreign keys should have the same name as the primary key they reference. Right? Okay, and that's just so that they match. Okay, so there are of course exceptions. Sometimes you may have to violate this guideline, and this is why they're not rules. These are guidelines. This guideline, if necessary, right? So, for example, if I wanted to model, say, a salesperson and a delivery person and a customer who is also a person in one table, I can't use person ID, right? So, in that case, I would have to say customer person ID, or better yet, customer ID. Salesperson ID, delivery person ID, right? And so in those cases, you would have to violate that because you can't have more than one column with the exact same name, right? let's see. You can define unique keys to ensure uniqueness on other columns, right? Generally what we do is we say PKs are going to be surrogate keys that are generated and managed by the database, right? And then other keys will be what are called natural keys, right? Social Security number, NUID, UUID, et cetera, that are not managed by our database, right? And if we don't control them, they should not control us. Again, the examples that we gave last time, if somebody screws up an NUID and they come to us and we've used it as a primary key in this table, and a foreign key in that table, and a foreign key in that table, and a foreign key in that table, it's going to be a huge freaking headache to update all of those, right? But if it's just one record in one table, that's easy, right? So don't let natural keys that are defined by somebody else, control your database, or you control the structure of your database, okay? Join tables should be used to model many relationships. Be sure that there is plenty of test or mock data in your database, right? There are plenty of tools, right? For example, Mockaroo. If you use that to generate your CSV data, guess what? It can also generate SQL insert statements instead, right? Or you can use any CSV to SQL or JSON or XML tool out there, okay? Right. Check and uniqueness constraints can be defined to ensure data integrity. But be careful, MySQL does not necessarily enforce uniqueness constraint. Check constraints. It does enforce uniqueness constraints, okay? At least that we've seen so far. All right, so let's formalize what we were talking about, or what we implicitly did this entire time when I was defining this database, or designing this database. We've lost it now, but that's okay. Yeah, let's just look at this one, right? Basically, there was a process by which I thought about, all right, well, this thing is a person, so I'm going to have a person table, but then they have emails. Do I store that in one column or 3 columns, or no, I need another table out there entirely? That process that I was going through in my head is called normalization, okay? And there are lots of normal forms, but we're only going to focus on the first 3 that Cod gave us. Do you remember Cod? Right. Edgar Cod from IBM, 1970, the inventor of the relational database management model, right? Relational data model, right? And we've got a little mnemonic device to remember this later on, so remember Cod. But they build on each other, right? We're going to look at first normal form, second normal form, and third normal form. You can't have those higher normal forms unless you have all of the lower normal forms. For example, if you don't have first normal form, then you cannot have third normal form. If you don't have second normal form, then you can't have third normal form. It's a transitive relationship there, right? So let's talk about first normal form first, because it's the most basic. And as stated, it says that each attribute, that means column, in a table has only atomic values, right? So for example, each column in a table represents one piece of data, and only one. It's much easier to understand these things if you can look at violations of it. Violation would be, of course, storing a series of emails in one column as a CSV data. Right. So, for example, email 1 at foo.com, comma, email 2 at bar.com, comma, foo at email.com, right? If I just put those in, then I'm returning all the way back to pre-1970, where we've got everything stored in CSV files and flat files, right? that would be a violation of first normal form. Another one that we tried or that we thought about doing was just simply having 3 columns: primary email, secondary email, tertiary email, right? That's not a proper one-to-many relationship, because it's what it is, it's a 1 to maybe 3 relationship, right? You could have, each one of these could be null, or primary email could be null and then secondary email is defined, or maybe primary email is defined but then we're wasting space on these 2 columns over here with null values, right? So the idea here is that you want a true one-to-many relationship. You should always create a true one-to-many relationship, right? Okay. So again, the best practice is to simply separate these out into their own tables, and the foreign key would then go to the child table, just like an email. Right? Now, in some instances, it's not entirely clear what the relationship actually is. If you remember last time, we looked at, well, what happens when you've got an address, right? Something like this. Is it a one-to-many relationship? Right? Is it a many-to-one relationship? Or is it a many-to-many relationship? Or maybe you think, no, it actually is a one-to-one relationship. I am going to go ahead and collapse this down into one table, right? Again, all 3 of those are, all 4 of those options are, or I guess 3 of those, 1, 2, 3, no, 4 options there. One-to-many, many-to-one, many-to-many, or one-to-one, right? All 4 of those options have benefits. All 4 of those options have disadvantages and advantages. And you'd have to like really think about that and whiteboard it and go back and forth, right? Ultimately, though, you probably want the most general type of relationship there, right there, like a many-to-many. Right? But again, it's up to your design decisions, and can you justify those design decisions? That's why we call it. That's why we like people to team up. If you don't team up, you can always do what's called rubber duck debugging. Have you heard of that before? Yes, no rubber. Okay, so I used to have one on my view up here. Now it's a dog, but you take a little rubber duck. This is why you might see a rubber duck above somebody's desk at some point, and you put it up there. And if there's nobody else to tell your design to, you start talking to the duck. Right? This is, or you've got a bug and you're trying to debug, and you start explaining it to the duck. And 9 times out of 10, your explanations, oh yeah, that's right, I shouldn't be doing that, or oh no, that's what I meant to do, but I'm not actually doing that, or vice versa. And so just explaining it to somebody else. 9 times out of 10, this is what happens when I'm helping a student, right? They're describing something, and then oh wait, yeah, I shouldn't be doing that. Like they figure it out themselves, because it's just the process of walking through that, and talking through that design, or talking through that bug, right? And so talking through this, at least with yourself or with a rubber duck or somebody else, then it'll become clear on what the relationship between an address and a person is, right? But in general, you should probably, for first normal form, you should probably create another table, at least one other table, okay? Second normal form, well, first of all, again, it has to be first normal form. And then the formal statement here is that no non-prime attribute, that is column, is dependent on a proper subset of prime attributes, right? And this is why I tell you to have primary keys everywhere. Because if you have a primary key that is auto-incremented, it gives you second normal form for free, right? You don't have to worry about second normal form after that. But again, understanding what a violation of it would be is maybe this. Suppose that you have a purchase record in a table, and it has a customer ID, a store ID, and a store address. This is going to be a prime column, and this is going to be a prime column. In other words, the combination of these 2 things uniquely identifies a sales record, right? And so the primary key would actually be 2 columns, and you can do that, right? But then that's where violations of second normal form come up, which is why, if you just follow my instructions, you'll always have second normal form for free, right? But in any case, this is not a prime column, store address. Now, does it depend on both of those things there? Store address certainly depends on store, right? The store ID, because that store exists at one location. But does the store address depend on the customer? No. And so we have a non-prime attribute here, the store address, that is dependent on a proper subset of prime attributes, just the store ID over here, okay? And that's a violation of it. And everything I just said, I'll go ahead and put into the notes here. Suppose the prime key is the combination of those two things. If you define a primary key as a combination, then you violate the store because the store address is dependent only on the second half, right? Often it is useful to define what are called compound keys. We did that, right? We did that in our join table over here. There's a compound key right there. The combination of the person ID and the account ID, right? But they should always be secondary keys, okay? Not primary keys, okay? Again, you just split everything out into its own table, right? That's the solution there, right? The address, the store address should clearly be some other table called address, right? All right, well, what's third normal form? Third normal form has to be second normal form, and transitively it has to be first normal form. But the statement is that no non-prime attribute, is transitively dependent on the key, okay? Here is a violation of that, okay? So we've got our annuity class, remember? And we've got a number of terms, years, and a monthly payment. And suppose that we stored the total value, which is the number of years times the payment times 12, right? If we stored all three of those things, that would be a violation. The total value is stored when it should actually be recomputed, right, based on the other two columns. The other two columns give enough data to determine the third, right? In other words, it is the third is transitively dependent on the first two, right? Because the first two, you multiply them together, multiply by 12, and you get the third, okay? This gives rise to possible data anomalies. If you change one of those columns, right, then the other two columns are now wrong, right? Or maybe at least one of the other two columns is wrong, right? So if I change the number of the term of years, I bump that up to 7 or something, then this total value has to be recomputed, right? If I change the monthly payment, then this total value has to be recomputed. If I change the total value, right, then it's completely out of sync with the other two variables there, the other two columns. So don't do that, right? And here's the summary that I was talking about, right? Every non-key attribute must provide a fact about the key, first normal form, the whole key, second normal form, and nothing but the key, third normal form, so help you COD, right? So we got to get this from, I swear to tell the truth, the whole truth, and nothing but the truth, right? And this is the mnemonic device to remember first, second normal form. And there's Edgar Cod again from 1970, okay? I think he's still alive, at least last time I checked. All right, so that is the end of databases, or at least database design in CRUD. There's a lot more. This is not a database course. We will only spend 2 weeks or 3 weeks on database stuff, right? If you were to take a whole database course, I don't know, do they have a data? IS&T would probably offer one. I'm not sure what it would be. But if you took an elective on databases, right? There's a lot more stuff to cover. There's something called triggers, right? And this is stuff that you would need to know if you ever become a DBA, right? What is a DBA? A DBA is a database administrator, all right? Sometimes they're given even administrator. Yeah, that's right. All right. Sometimes they're given more fancy names now, like business intelligence, right? Or I don't know, business analytics, or whatever else is or big like data scientists now is what we're calling them. So these names change depending on the company you go to or the culture you're in or whatever. But at the heart, they're all database administrators because they're writing SQL queries all the time, right? Or they're handling data and they're shuffling it around, making sure that it's good all the time. Or they've got a bunch of data that they need to import. So I need to write a script to generate a bunch of SQL statements to make their data model compatible with our data model, et cetera, right? And so these are the kinds of things that you need to know if you're a DBA. Triggers are event-based actions in a database. So suppose that you have stored in like a password stored. You shouldn't do this, by the way. But suppose that you have a login system where you want to keep track of the last time that they logged in. First of all, the system logs are way better use of this, but you can store them in the database and say, okay, they've logged in. I will trigger that and say that the last successful login was, and then date time stamp that, so that I can run a report on, how many people logged in today or something, right? Those are triggers that if you update a column, then it triggers another subroutine that does something in the database, right? Another one would be views, right? That we've not talked about, but views are basically read-only tables in a database. So if you've got a bunch of data that, okay, this person comes in, they say, I need access to this data, and this data, but I don't want to give them access to this data and this data, right? So what I'll do is I'll design a view that looks like a real table, but it's not. It just gives them a subset of those columns, of subset of that data. And not only that, but it's read-only, because I don't trust them. I don't trust them to screw up my data, so I give them read-only access to a fake table with only the data that they're allowed to access. They can query that all they want, right? I don't care, because I was able to control their access to it. In fact, this is not just a good practice for people you don't trust. Never trust yourself either. If I were writing an application, I would probably write two parts. The part that would actually insert data or update data or destroy data, and then I would write the part that actually selects data. And I would only give read-only access to that part, right? Because I don't want this part ever screwing up any data in my database. And then I would pay extra careful, close attention to this part of the application, right? So you can have applications that one part of it is only given access to a view, and the other parts are actually given to the CUD, the create, update, and destroy part of CRUD. Right? Temp tables are another really nice thing, where you can treat basically. We haven't talked about transactions, but we will. In fact, let's talk about transactions first. A transaction is an atomic operation on a database, right? That supports the ACID principles. Right? Principles. So let's go ahead and get rid of this, and let's talk about the ACID principles. Right? It's atomicity, consistency, isolation, and durability. So this is by now our 20th acronym, right? The ACID principles. A transaction is an atomic operation on a database. So suppose that I wanted to insert 3 records. I could wrap that up in what's called a transaction. Everything goes right with the first record. Everything goes right with the second record. But something goes wrong with the third record. Because it was wrapped up into a transaction, that error rolls it back to the beginning like nothing ever happened, right? That's because it's atomic, right? It's an all or nothing thing, right? All 3 of those things happen or none of them do. There's nothing to prevent you from wrapping up every single one in its own transaction, so you have 3 transactions, 3 queries. But if you want to say that, okay, this all needs to happen or none of it should happen, right? That way you ensure consistency. Consistency is all the rules that you've defined in your database, all those check constraints, all of those foreign keys, all of those rules that you put in your database. It's guaranteed that before a transaction, they're all followed. After a transaction, they're all followed. But maybe during a transaction, it shuts things off. It shuts off safe mode or something to do the transaction, but then it turns it back on. That's the kind of idea. They ensure that transactions are in isolation. That if we have 2 apps that come in at the same time, or 2 threads, or 2 processes, or whatever, and they start reading the database, they get their own view of the database. So if this transaction starts doing something with the data, this transaction is completely unaware of what the other transaction is doing. Those 2 transactions, all transactions are done in isolation, so that they're not stepping on each other's toes. Durability is that it ensures that if you have catastrophic failure, somebody kicks out the plug or something, and then you bring the database back up, all of your rules and all of your data will still be 100%, right? That means that the rules are 100%. Now, of course, if there was inside of a transaction when somebody caused a catastrophic failure, right, then it's an all or nothing thing, so it rolls back to the beginning. That new data didn't happen, right? But all of your rules are still enforced, right?
So it would
Yeah.
prevent, like, if you're in the middle of an operation, then you wouldn't just have half-baked.
Exactly, exactly. That you don't have half-baked data insertions or processing.
Okay.
It rolls it back to like right before you even began in that transaction, before you even began, and it's like it never happened. I don't generally cover how to do transactions over here because every single MySQL vendor or every single SQL vendor does them differently. So what is MySQL transaction? We can take a look at transactions in MySQL are done with what? Okay, there it is. Start transaction, right? Note that begin or begin work are aliases. Okay, so those are, and then if you want to commit it, you commit it. Otherwise, if you want to roll it back, you roll it back, right? So start transaction, commit, and then roll back or auto commit is the default. So every time you run something in MySQL Workbench, you're doing it in one transaction and that's it. Right? It's everything is done, right? One transaction per query, I should say. But otherwise, if you wanted to do your own transaction, I don't know. I've copied this, so let's go ahead and do something unsafe. Start transaction, drop database, cberk3, right? And then roll back, because I don't want to actually drop my database. Start transaction. I think that this will work, but let's find out. All right, so do the entire thing. Roll back, good. Show tables. Oh no, I need to use cberk. There we go. No data, no, I said use cberk. All right. Oh no, it actually did drop it. All right, it didn't actually work. I don't know why. Maybe I had to do all three of these things. Nope, it's only rolling back. All right, so I just lost everything. That's all right. I've got it over here. All right. Don't make that same mistake without backing your stuff up, right? I copied and pasted it over here, right? This is why you should use GitHub as well, right? All right, so I don't know, maybe I'm not doing something right over here. Undo the changes of a transaction by reverting the database to the state before the transaction starts. Maybe it doesn't work on dropping the entire database. There, we can see if it works on an individual one. Let's go ahead and grab that stuff and run it all again. Okay, create database. cberk3 since I dropped it. All right, run everything again. Oh no, num shares. Oh. Okay, I should take out that check constraint now. Da-dun, 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 there. All right, run it all again. I need to take out that comma too. There we go. Run it all again, great. All right, now let's go ahead and start transaction, right? And what I'll do is delete from email where email ID is greater than 0. That's a way of getting around the safe mode. And then end or roll back. All right, it's saying that I need print. This doesn't sound right, but whatever. All right, and I'm gonna get rid of all of this. Okay. Oh yeah, the email table doesn't exist. Email. There we go. All right, so select everything from email. Oh, good. It works on data. It just didn't work if you if you blow away your entire database, apparently, right? But I didn't actually end up deleting anything because we started a transaction, I did something dangerous, and then I rolled it back. The opposite of that would, of course, be commit. Let's go ahead. Now there are no emails left. They're gone, period. There's no undo. Right? That's why you have a database backup over here. Right? But otherwise, roll or commit or roll back. I'll go ahead and put that in the notes so that you have it, so that you can see what it actually looks like in SQL, or at least MySQL. There are, I think that there are other keywords. If you were to go like move to a SQL server or a Microsoft server or something, there are probably different keywords there that are used. But those are transactions. Then what got me off that tangent there was that you also have temp tables, right? And temp tables are temporary tables that can be created within a transaction to make data processing easier. So if you've got this table and that table and that table, I'll dump them all to a temporary table so that I only have to operate on that temporary table. It makes really complicated queries a lot easier in some cases, but you can create temp tables. You can also do stored procedures. Stored procedures are basically functions that you can define and reusable SQL code that you can treat like a function. We've already seen a couple of functions, right? Sum, count. You can define your own functions. But again, it goes beyond the scope of what I want to do. And we're not going to be DBAs after only 3 weeks here. Because you also have, it's a full programming language. You do have loops. You do have variables. They're called cursors. You have all the basics that you would have in any programming language. You have functions. You have et cetera, right? So you have all those things, but they're not things that I'm going to talk about, right? Because we can't talk about everything. One last thing that I'll mention is what are called soft versus hard deletes, right? So what is a hard delete? A hard delete is a result of a delete statement. In other words, there's no undo, no recycle bin, right? You cannot recover that data, right? A soft delete would have an is active column, Boolean column in a table, right? So how would you delete? Delete would not actually delete. It would actually set update record set is active equal to false, right? Oh, for that record, where blah, right? Something like that. Why would that be helpful? Why that's called a soft delete because it doesn't actually delete the record, right? It just makes it inactive. Then when you select, you only pull active records, right? So it looks like it's deleted, but it's not actually deleted. Why would this be nice? You have a bad ID10T user. Do we know ID10T users? ID10T users?
Oh.
Who, despite all of your interface design, they delete a bunch of records. You pop up a window that says, you're about to delete the records. Are you sure? Yes. This operation is permanent. Are you absolutely sure that you want to do this? Yes. And then they call you up and say, I didn't actually mean to do that. And so what you do is you say, okay, well, it might take us a couple of hours, might take us a couple of days, but I'll see what I can do. You sit there and you relax and you do whatever you want. And if you're an independent contractor, you bill them for a minimum of 10 hours at $300 an hour, right? And then you go in and you say, okay, I'm going to go ahead and reset those is actives to true because they never actually deleted the records, right? Because you designed it with a soft delete. And I've done this before where I knew, no, we're going to have a lot of bad users here. I'm going to go ahead and make sure that they're soft deletes so that when they call me up and say, oopsies, I'm going to go ahead and be able to restore those records, right? And I knew that I could always restore them from a record because we made regular database backups every 1 hour or something like that. But then that means that there might be an hour in there in which we can't restore. Or I'm going to have to go through and cherry pick the records that they want to restore and make sure that I'm not screwing up any records that have been created in the last hour, right? So this has saved me an inordinate amount of time, right, by doing this. Don't do it it's not necessary for your projects, right? But it is something that you should realize that it can make you a hero overnight. Or you can say, you can bill them for $300 an hour at 10 hours minimum, right? Because when you're an independent contractor, you write the contract, right? And they sign the contract or they don't get the work, right? Anyway, yeah. So that's all of the, oh, I guess one more tip, I'll go ahead and reiterate here that generally you want to use a single table inheritance strategy with databases versus OOP models. Again, the database model, relational model predates OOP by at least 20 years. They weren't thinking about inheritance or polymorphism or anything like that. And so you have to reconcile these two different data models. And the reconciliation is going to be your single table inheritance strategy. It's the simplest, right? You could, if you wanted to, right? You could do a table per class or table per subclass strategy, but it's more complicated than it needs to be. In other words, Yagni. At this point, do we remember Yagni yet? No? You ain't gonna need it. So, don't do it. Our entire discipline is full of nice acronyms, right? Nice acronyms that you can pull out at any time. Solid principles, OOP, ACID, CRUD, right? And so when you start, talking with other professionals, right, and they drop a Yagni on you or something like that, you'll understand what they're talking about. Right? Otherwise, just play dumb and then say, or just play smart and then look it up later. What the hell's a Yagni? Right? All right. So, any questions on databases, database design? Because what we're going to do next, when we come back next week, we're going to stay in the same module here, but we're going to end up trying to programmatically connect to a database, right, using an API. And our API is going to be JDBC, Java Database Connectivity API. Any language out there is going to have the same exact thing. Any language is going to have some sort of a library, an interface library that connects you to a database. Not necessarily to an SQL database, not necessarily to a Postgres database, just a database. Because under the hood, it's taking care of all of the details, right? So that you don't have to program towards that MySQL database or that Postgres database or the SQL server. Instead, you program towards an interface, and then it's the interface's job to go out to a specific database. Do you remember what that's called? The solid principles? Dependency inversion, right? So that we don't have to rewrite the code if we change our database from MySQL to Postgres. We program towards this API, this application programmer interface. Right? We don't program towards MySQL. Right? But I'll go ahead and get you started on that on next Tuesday. All right, any questions? All right, then I'll see you upstairs if you're still working on Lab 7 or want some feedback on your design for Assignment 2, which is due this Friday. And a reminder that Assignment 2, if you're going for that bonus on Assignment 3, those CSV files are due a week ahead of time. Put them in your Assignment 2, and we'll take them there. Okay?